Okay, in this section, we put in together everything we found out about first and second derivatives to get an idea about what graphs look like. Because if we really break down, there's like four things that can happen here, and they're kind of interesting to think about, but it does help to look at them all together. All right, let's say if something has a first derivative that's positive versus something has a first derivative that's negative. This would mean that it's increasing, and this would mean that it's decreasing. So these are uphill and these are downhill. So uphill, downhill. But then the other thing that we've looked at can happen is if we have something that has a second derivative that's positive, that means that it's concave up. Or if we have a second derivative that's negative, it means that it's concave down. So what would these things look like? So let's say I have something that's uphill and concave up. So it would look something like this, right? It's increasing, it's going uphill, but it's also concave up. So what if I have something that's increasing but concave down? So this is kind of getting steeper as it goes. It's increasing at an increasing rate. Interesting thing to think about. This one is increasing at a decreasing rate. So still going uphill, but it's getting less steep as it goes. It's also concave down. All right, so then what about the downhill ones? So we could also have a first derivative is negative, meaning it's decreasing. It could be decreasing and concave up. Kind of looks like a little slide, right? It's concave up shaped. It's decreasing. It's getting less steep kind of as it goes, so you'd slide down. All right, then we could also have, what if they're both negative? So concave down and decreasing. So that looks a little bit more like falling off a cliff. Like it's decreasing, right? You're heading down, but it's decreasing at a decreasing rate. It's getting, or increasing rate, it's getting steeper and steeper and steeper. So here's all the positive first derivatives. Here's all the negative first derivatives. These two are both concave up and these two are both concave down. So there's really only kind of like four shapes that can happen. But if we put those all together, we can get some pretty interesting graphs, right? If we had something, and you can usually kind of like see them visually pretty well. Even if we just try to visually split this up, the place where it switches from concave down to concave up, so this part all kind of looks concave down, is a little bit harder to eyeball than the maximum minimums, and we don't eyeball them. We set the second derivative equal to 0, but the places where it switches from one to the other, so let's say somewhere around maybe here, just visually, it's concave down and then it switches to concave up. That is what we call the inflection point, and it's where the second derivative is equal to 0, right? If it's because the second derivative is concave down will be negative, then the second derivative switches to positive. So at the inflection point, that's the place where it's actually equal to 0 for a second. And then our first derivative, we can see a little bit easier. Here's the places where the first derivative equals 0. And those are the only places where it can switch from increasing to decreasing, right? So it looks like here it's increasing. Then it goes to decreasing for a little while, and then it goes increasing again. So notice that gives you kind of like four interesting intervals on this, and this is what a lot of the questions will ask about is, over here, it's increasing, but concave down. So positive first derivative, but negative second derivative. So increasing and concave down. Then from here to here, it's decreasing, right? It's downhill, but it's still concave down. So that would be the first and the second derivative are negative. And then after the inflection point, it switches for a second. It's still decreasing. So first derivative still negative, but it switches to concave up. So now the second derivative is positive. And then over here it goes back to increasing. And then the second derivative, it goes concave up after the inflection point. So notice here's like an example, all four of those scenarios kind of connected together. Increasing, concave down, decreasing, concave down, decreasing concave up and then increasing concave up. And so this is what they mean by curve sketching is like if you know all these things about the first and second derivative, you can get a pretty good idea of what a graph looks like without actually graphing it. So some of the questions they get into, they ask you the same stuff. They want you to tell them where these intervals start and stop. Like where does it get interesting, right? Because right here, and right here is when the graph makes a change from one to the other. So if you had to describe this in intervals, I'd make, everything from negative infinity up to this interval, and here all the way to infinity. So there's kind of 4 interesting intervals on this one. All right, so let's try it with an actual function, like in one of the homework questions. All right, so the first thing they say is they actually tell you there's 4 important intervals on this one. So places that are critical numbers or not defined, which is also another place that a critical number can be. So to find critical numbers, we have to take our first derivative and set it equal to 0. At least they already wrote this as an exponent. That makes it easier to take the derivative. So derivative of 7x is 7. Derivative of negative 3x to the negative 1 is, or 3x to the negative 1 is negative 3x to the negative 2. And this is the same thing as over x squared. Maybe when we get to the solving it for 0, it'll be easier to have it written this way. All right, so if we set the whole thing equal to 0, we could maybe add the 3x to the other side term. I just picked that one because it's negative. And then multiply by both sides by x squared to get that out of the denominator. And then divide both sides by 7. So 3 over 7 equals x squared. And so the square root property tells us plus or minus the square root of 3/7 equals x. So 2 irrational numbers, like decimal something. I think you can put these, or you can put the decimal version, should be okay. It's approximately plus or minus 0.654. 65. Right, you can't take the square root of 3 or 7, so it's going to be rounded, or you can leave it like this, probably in the answer box. And then one other point that's important here is notice from the beginning, we can't plug 0 into the denominator because we'd be dividing by 0. So our critical points are the places where the derivative equals 0 and also anything that's not in the domain. And so we have to make sure we put x equals 0. The main reason for that is think like vertical asymptotes. If another way that you could switch from increasing to decreasing or vice versa would be if you had an asymptote, but maybe your function was going like up here, and then on the other side, see how that switched from increasing to increasing, but this one was concave up and this one's concave down. Or if it went like this, it switched from increasing to decreasing. So those points are also important because the graph could do something weird around this point. All right, so there's our important intervals. And then they just ask whether it's increasing or decreasing. So totally up to you. You can graph it, or you can put it in your calculator, or you can put it in the table of your calculator, or you could do test points. So if we know that here's the place where they could switch from increasing to decreasing, then all we care about is, make a little table to get our thoughts organized here, we care about is the derivative positive or negative, kind of in between those points. So we had what? Negative 0.65, 0, and positive 0.65. So here's the places where the derivative is equal to 0. I'm kind of putting these in the threshold. So then you could pick any point in between. So maybe something like negative 0.5, maybe positive 0.5, right? Just because it's between 0 and 0.65. Maybe like 1. You could pick 100 if you wanted to. It doesn't make a difference. You just have to be on the other side of this number. And we could just test, is the derivative positive or negative at those? So our derivative was 7 minus 3 over x squared. So if I put negative 1 in there, I get 7 minus 3 over 1. So I get 4. 7 minus 3? That looks right. So 4. But all I care about is that that's a positive number. So that's telling me that it's increasing on that interval. And then if I put in something like negative 0.5, I get a negative number. So that tells me it's decreasing. And then if I put positive 0.5 in, I actually get the same number because the squared gets rid of the negative. So also negative, so there's a decreasing interval. And then if I put in 1, I get the same thing as if I put in negative 1. I get 4. So it's positive, so there that interval is increasing. So there's one way to tell, or you guys have your calculators, you can just graph it. On the screen share, I don't have a super easy way to switch over to a calculator screen. I have one, it's just a little bit cumbersome. So, all right, and then we could talk about concavity. So we care about, for talking about concave up or down, the second derivative. So here's the first derivative. Just jot it down so we don't forget what it was. So if we take the derivative again, that would be the second derivative. So derivative of 7 is 0 because it's a constant. Negative 2 times negative 3 is 6, x to the negative 3. So notice this one, there's no places where this equals 0, like if you try to solve, but we could still try, there's still a critical point in this because it's not defined at x equals 0. So we could still do the check and see, is the second derivative positive or negative? What happens on each side of 0? So picture if I put any negative number and any positive number. I'll just pick 1 because they're easy to plug in. If I put 1 in this, I get 6 over 1, so 6. And if I put negative 1, I get 6 over negative 1, so negative 6. So this tells me, since this is negative and this is positive, it tells me that it's concave up from 0 to infinity, and it's concave down from negative infinity up to 0. So there, if we did want to take all that information, they don't ask you to in the question. They just have you pick increasing, decreasing, concave up, concave down. But if you did want to put all that information together, you could get a pretty decent picture of what this graph looks like.